Okay, welcome to the class. Today is the second lesson of chapter 1. In today's lesson, we'll have a look at two topics, alkenes and alkynes, and then aromatic hydrocarbons. So we have, as we learned in the previous section, all of the carbon-carbon bonds in an alkane are single bonds, right? In other organic compounds, however, double or triple covalent bonds connect some of the pairs of carbon atoms. A hydrocarbon containing carbon-carbon double or triple bonds is called an unsaturated hydrocarbon because each molecule contains fewer than the maximum number of hydrogen atoms. Unsaturated hydrocarbons have a variety of uses in industry and everyday life. For example, ethylene, commonly known as acetylene, is the fuel used in welding and cutting torches. This molecule contains a triple bond between its two carbon atoms, which is shown here in figure 1. Ethylene, another unsaturated hydrocarbon, is used in agriculture to help ripen fruit more quickly. Ethylene contains a carbon-carbon double bond, which is shown here in figure 2. Note that each carbon atom always has 4 bonds. In an ethylene molecule, each carbon bonds to 3 atoms, 1 carbon and 2 hydrogen atoms, but the carbon-carbon bond is a double bond. In ethylene, which is shown in figure 1, each carbon atom is bounded to only 1 hydrogen atom. The remaining 3 bonds connect to the other carbon atom. In this lesson, we will learn about hydrocarbons that contain multiple bonds. So, a hydrocarbon that contains at least 1 carbon-carbon double bond is called an alkene. So note that the suffix we use here is ene. Alkenes with 1 double bond have the general formula CnH2n. The simplest alkene is ethene, C2H4, which is shown here in figure on the top left. An unsaturated hydrocarbon that contains at least 1 triple bond between 2 carbon atoms is called an alkyne. Alkynes with 1 triple bond has the formula CnH2n-2. The simplest alkyne is ethine, which is shown here in the figure on the bottom left. Scientists use the general term aliphatic hydrocarbon to refer to a compound that has a structure based on a straight or branch chains or rings of carbon atoms. Alkenes, and alkynes are all aliphatic hydrocarbons. Okay, so similarly, we still need to learn how to name alkenes and alkynes. Like alkanes, unsaturated hydrocarbon names are based on the longest hydrocarbon chain. The name of alkene ends in the suffix ene, and the name of an alkyne ends in yne. For example, the alkane C3H8 is called a propane, right? The alkene C3H6 is called propene, and the alkyne C3H4 is called propane. We're going to have a look at some tutorials which describe in detail the process for naming and drawing the unsaturated hydrocarbons using the UPAC convention. Alright, remember, we're still gonna use these prefixes and the prefixes to describe the numerical roots based on how many carbon items are in the straight chain, and use the prefixes on the bottom to describe the number of entities of the same kind. So you should have this on your journal, right? Okay, next let's have a look at some tutorials. Tutorial 1 is to learn name and draw alkenes and alkynes. The rules for naming alkenes and alkynes are similar to those for alkanes. The first step is to identify the parent chain or ring that contains the multiple bonds. Number 2 is to identify whether the chain or ring contains a double bond, in which case it's an alkene, or a triple bond, in which case it's alkyne. If the hydrocarbon chain has more than one double or triple bond, add a suffix to show the number of multiple bonds, such as diene or triene. Number 3 is to number the parent chain or ring so that the first carbon item involved in a multiple bond has the lowest possible number. Write this number before the suffix. This is only necessary if there are more than 3 carbon items. And the last step is to number and name any substituents using the same rules as were used for alkanes. If the double or triple bond is in the middle of the chain, start the numbering from the end nearing the substituent group. Are you clear? Well, don't worry, we'll have a look at some examples to illustrate this method, okay? So basically, following these rules, suppose we have a molecular formula CH2CH3. This is called put 1 in, and CH3CH3 is called put 2 in. You may encounter an older naming method in which the number of the first carbon to include the multiple bond is written at the beginning of the name. For example, put 2 in would be called 2-butene. As another example, a chain of 8 carbon items with double bonds at the second, fourth, and sixth carbon items will be named octa 2, 4, 6 triene. An 8 carbon chain with triple bonds at the second, fourth, and sixth carbon items is octa 2, 4, 3 triene. Are you clear? Okay, next let's have a look at some sample problems. So in the following sample problem, we will learn how to name unsaturated hydrocarbons by examining their structural formulas. And then after that, we'll learn how to draw their structural formulas from their names. Okay, let's consider this problem here. Determine the correct name for each of the following compounds. We have 1, 2, 3, 4, A, B, C, D, 4 different compounds here. Are you able to give their name? Okay, again, I'll lead you through the first one and leave the other 3 for you to solve, okay? Okay, let's have a look at the first one. Apparently, this is a alkyne, right? Because we have a triple bond here. So the first step is to identify the parent chain or ring that contains a multiple bond. In this compound, the longest chain is 7 carbon atoms, right? With 1 triple bond. So the root name contains hept. Number 2 is to identify whether the chain contains a double or triple bond. If it's a double bond, we have an alkene. And if it's a triple bond, we have an alkyne. Apparently, the molecule contains a triple bond, so it's a alkyne. Its name contains the suffix YNE, and therefore the root name is heptine. Step 3. Number the parent chain so that the first carbon atom involved in a multiple bond has the lowest possible number.
Is Dylan here?
Yes. Write this number before the suffix, then the triple bond is attached to the third carbon atom, hept3-ine. And the last step is to number and name any substituents using the name rules, using same rules as were used for alkanes. If the double or triple bond is in the middle of a chain, start the numbering from the end nearing the substituents. So here the ethyl group is bounded to the 5th carbon atom in the chain, right? So we have a 5-ethyl. Then this compound is named 5-ethyl hept3-ine. Are you clear now? Okay. Now it's your turn to try to name the other 3 compounds here. Alright, have you finished? Okay, let's have a look at the other three. Okay, question D. So apparently the parent chain or ring contains 5 carbon items, right? So we should use the prefix penta or pent. That depends on whether it's followed by a vowel, right? Remember? So let's have a look at the prefixes here. If followed by a vowel, you should drop the A. Otherwise, if the prefix followed by a consonant, you should add an A there. Okay? Be careful with that. So here we have 5 carbon items, so we should use the prefix penta or pent. Step 2 is to identify whether the chain contains a double bond or triple bond. So there are 2 double bonds, right? So it's pentadiene because diene start with a D. D is a consonant, so we should use the prefix penta instead of pent. And last step, numbers of parent chain so that the first carbon item involved in a multiple bond has the lowest possible number. So the double bonds are the first and third carbon items, so this compound is called penta-1,3-diene. Are you clear? Okay, how about the next? What's its name? Okay, first of all, there are 5 carbon items in the chain, right? So again, we should use the prefix pent or penta. Then identify whether the chain contains a double bond or triple bond. So there is a 1 double bond apparently. So the compound is pentane. So this time we need to remove the A, right? Because pent followed by E, and E is a vowel, so we should use a pent. So the base name is pentane. Next step is that the double bond is between the first and the second carbon item. So the name is pent-1-ene. Last step, this compound contains a chlorine item bounded to item 3. Therefore, this compound, the full name is 3-chloropent-1-ene. Did you get it? Are you clear? Okay, now let's have a look at the last one. That involves a ring structure, so we should use a prefix cyclo, right? So the ring contains 5 carbon items, so we should use a prefix cyclopent or cyclopenta. Next, there is 1 double bond, so it's a cyclopentene. Next step, in a ring, the carbon items are always numbered so that the multiple bond is between carbon items 1 and 2. So we have the base name, now cyclopent-1-ene. Next step, number and name any substituents using the same rules as were used for alkanes, which we learned yesterday. Whichever way you count around the ring, the methyl group is attached to carbon item 4. So this compound is therefore named 4-methyl cyclopent-1-ene. Are you clear? Any questions? Okay, if not, let's have a look at how to draw the structure of alkenes or alkynes. When we are given the name of alkene or alkyne and asked to draw a structure, the steps are similar to those for drawing a alkane. You can simply follow the following procedures. Step 1. Draw the parent chain or carbon ring from the last part of the compound name. Step 2. Identify the carbon item where each of the multiple bonds and substituents is attached. Number 3 is to draw the multiple bonds and substituents at the appropriate locations. Okay, next let's consider sample problem 2. Draw the structural formula of each of the following compounds. A. 2-methyl penta-1,4-diene. be 4,5-dimethylheptatoluene. So I'll lead you through the first one and leave the other one for you to solve. Okay? Okay, let's consider question A here. Remember, step 1 is to draw the parent chain or carbon ring from the last part of the compound name. So the name here is penta-1,4-diene, tells us that the longest carbon chain is 5 carbon atoms, right? Then identify the carbon atom where each of the multiple bonds is attached. The name diene indicates that the compound contains 2 double bonds. The number 1,4 tells us that these double bonds are between the first and second and fourth and fifth carbon atoms. The 2-methyl part of the name indicates that the molecule also contains a methyl group bounded to the second carbon atom. Therefore, we can draw the multiple bonds at the appropriate locations. The structure of this compound is as follows. Okay, have a look at the solution here. Any questions, just let me know, okay? Okay, if you don't have any question, now it's your turn to complete question B here. Okay, have you finished? Okay, let's have a look at the solution together. You can compare your solution with mine here. Step 1, the longest carbon chain is 7 carbon atoms, right? And step 2, it contains 1 triple bond between the second and third carbon atoms. It also contains 2 methyl groups bounded to the fourth and fifth carbon atoms. Then we can draw the multiple bonds and substituents at the appropriate locations. So the structure of this compound looks like this on the bottom. Now, do we have any questions? No? Alright, next let's have a look at another concept which is called cis-trans isomerism. Well, if you use the molecular modeling kit to build isomers of pentane, which is discussed in the previous section, we probably noticed that you can rotate the carbon atoms around the single bond, connecting each atom. As a result, you could create many 3-dimensional models that look different but are actually identical, having 5 carbon atoms in a chain, right? However, when you made the models of pentene, you may have noticed that you cannot rotate the carbon atoms around the double bond. Therefore, the groups on different sides of a double bond are in a fixed position relative to each other, which is shown here in figure 4. This figure shows 2 pentane structures representing 2 different compounds because the molecule cannot rotate around the double bond. The 2 pentane structures in figure 4 are stereoisomers. Stereoisomers have the same kind and number of atoms bounded in the same order but have different arrangements in space. Stereoisomers cannot be changed from one another by simple rotations. bonds would have to be broken and reformed. Stereoisomers are distinct compounds with different properties, such as different melting points. And in this course, we'll use the term cis and trans, to describe the positions of the parts of a molecule around the double bond. A cis isomer has matching alkyl groups located on the same side of the double bond, whereas the trans isomers has a group located on opposite sides of the double bond, which is shown here in figure 5. Here. Look at the concept shown in figure 5 here. When we refer to the sides of a double bond, we mean the two sides of the molecule divided by a line running along the double bond. We use the word cis or trans naming system only when two of the substituents are the same. So in this case, methyl groups, and only for alkenes. Well, you should also note that the U-Pack conventions use a different system, incorporating the letters E and V, which you might see in other textbooks. So we'll talk about this later, okay? Alright, so following this discussion, let's have a look at a tutorial. Naming and drawing cis-trans isomers. In this tutorial, we will practice naming and drawing cis and trans isomers of alkenes. Okay, for example, suppose we have a figure here showing two stereoisomers of pent-2-ene. Can we name each stereoisomers? Use the cis and trans naming format. So I'll give you 1 minute to think about this, and then we'll have a look at the solution together, okay? Okay, have you finished? Let's have a look at the solution together. So here, in figure 6a, the substituent groups are bound to the same side of the pair of the double bound carbon atoms, right? Therefore, we should use the prefix cis. So its name is cis pent-2-ene. In B, figure B here, the two substituent groups are on the opposite sides of the double bond, so we should use the prefix trans. So its full name is trans pent-2-ene. Did you get it? Okay, and you should also make sure you are also be able to draw the structural formula given the name of the compound. When drawing structural formulas for compounds that are stereoisomers, follow the same steps that you have already practiced for drawing structural formulas. The only difference is the position of the part of the molecule on either side of the double bond. So we can simply follow these procedures here. And let's have a look at another problem. Can you draw the structural formulas for cis-1,2 dichloroethene and trans-1,2 dichloroethene? Again, I'll give you 2 minutes to think about that, and we'll have a look at the solution in 2 minutes. Okay, let's have a look at the solution together now. First step, we know ethene contains 2 carbon atoms with a double bond between them, right? And for ethene, the double bond can only be in one place, between the 2 carbon atoms. From the name of the compound, you know that it contains 2 chloro atoms. You also know that each chlorine atom is bounded to a different carbon atom. Therefore, add 2 chlorine atoms, one on each of the carbon atoms. The cis isomer will have the chlorine atoms on the same side of the double bond. The trans isomer will have the chlorine atoms on opposite sides. Well, you could just think of cis as being like sisters, which means side by side, and trans means across, as in transatlantic. This will help you to remember the meaning of cis and trans, okay? And for the last step, we don't have any other substituents to add. So their structural formula looks like the graph shown here. Any questions? Make sure you can do this by yourself, okay? Alright, next one. We're going to have a look at reactions of alkenes and alkynes. Okay, first of all, the concept of a functional group. Functional group is a specific group of items within a molecule that affects the properties of the compound, such as solubility, melting point, boiling point, and chemical reactivity with other elements or compounds. Multiple bonds are considered to be functional groups because they affect the properties of the molecules that contain them. For example, alkenes and alkynes are more reactive than alkanes. The double-bonded and triple-bonded carbon atoms are more likely to take part in reactions because the multiple bonds are less stable than single bonds between carbon atoms. One common type of reaction that alkenes and alkynes undergo is an addition reaction. In an addition reaction, two molecules react to form one. The multiple bonds in alkenes and alkynes enable the organic molecules to react with hydrogen. The addition of hydrogen is a type of addition reaction known as hydrogenation and results in the hydrocarbon becoming saturated. The concept is illustrated here in figure 7. For example, a unsaturated molecule of ethene becomes saturated by the addition of hydrogen atom on either side of the double bond. Then a molecule of ethene is formed. Are you clear? And hydrogenation, in which hydrogen atoms are added on either side of the multiple bond, can occur with alkenes, alkynes, or cyclic alkenes. These concepts are illustrated in figure 8 here. So figure A shows propene reacts with hydrogen to form propane. Figure B shows propane reacts with 2 moles of hydrogen per mole of propane to form propane. And figure C shows cyclohexyl 1,3-diene can react with hydrogen to form cyclohexene. These are examples of the reactions that involve alkenes or alkynes. Any questions? The alkene or alkyne gains atoms from the reacting molecule but does not lose any atoms. Addition reactions may also occur with halogens, hydrogen halides, such as hydrogen chloride and water. In a halogenation reaction, a halogen such as bromine or chlorine reacts with an alkene or alkyne, which is illustrated in this figure 9. The halogenation of alkene produces an alkyl halide. The halogenation of an alkyne produces a halogenated alkene, or if excess halogen is present, a alkyl halide. A hydrogen halide, such as hydrogen chloride or hydrogen bromide, may also react with alkene or alkyne. This reaction is called a this reaction is called a hydrohalogenation reaction. The resulting compound includes both the halogen and the hydrogen atoms and may be a halogenated alkene or a alkyl halide. And further, in a hydration reaction, water reacts with an unsaturated hydrocarbon. This reaction produces a type of organic compound that contains a hydroxyl group, or /OH. We'll talk about the hydroxyl group later in the future lessons. So this compound is called an alcohol. Again, we'll talk about alcohol in our future lessons. So for example, this figure here shows in this hydration reaction, ethene reacts with water in the presence of a catalyst and acid to form ethanol. Ethanol is a type of alcohol. Okay, so if we look at figure 8 and figure 9 here again, in all of these reactions, the substances that is added to the hydrocarbon, for example H2, CL2, or Br2, is made up of 2 identical items. Therefore, only one possible product can form in each case. For example, we could switch the positions of the two chlorine items in 1,2-dichloropropane, which is shown here in figure 9a. But the product would be the same substances. In contrast, hydration reactions, which is shown here in figure 10, and hydrohalogenation reactions add two non-identical items to the multiple bond. Therefore, more than one product is possible, right? For example, in figure 11 here, this figure shows that when a hydrogen halide reacts with an alkene, two different products are possible. You could either have two bromobutene or one bromobutene. So which one is the main product? That is a question to ask, right? How we can predict which product will be formed. And a rule called Markov-Nikov rule provides guidance on how the items will be added to the double bond. Markov-Nikov rule is as follows. When a hydrogen halide or water molecule reacts with an alkene, the hydrogen item will generally bound to the carbon item in the multiple bond that has the most hydrogen items already bounded to it. Are you clear? So Markov-Nikov rule applies to hydrohalogenation of both straight chain and cyclic hydrocarbons, which is shown here in figure 12. It also applies to hydration reactions. For example, in figure 12, we know according to Markov-Nikov rule, the hydrogen item from the hydrogen chloride molecule bounds to the carbon item that has the most hydrogen items already attached to it. Despite Markov-Nikov rule, small quantities of the other product will be produced. If both of the carbon items have the same number of hydrogen items, an equal mixture of the products will be resulted. Sometimes a chemist may need to perform a hydrohalogenation or hydration reaction in which the hydrogen item is added to the carbon item that has the fewest hydrogen items already bounded to it. Therefore, chemists have developed strategies to overcome Markov-Nikov rule. They can use catalyst or other reaction conditions to change the expected outcome of a reaction. Okay, now let's use this rule to predict products of addition reactions. Let's have a look at a tutorial here. We can use the familiar skills of writing and balancing chemical equations along with strategies for naming organic compounds to predict the main products of addition reactions. Just remember to look carefully at the multiple bonds in an organic reactant and consider Markov-Nikov rule to establish where each item will be placed in the product molecule. Okay, let's have a look at sample problem 1 here. Can you predict the major product of a hydration reaction of 2-methyl-pent-1-ene? Major product. Okay, I'll give you 2 minutes to think about this problem first, and then we'll have a look at solution together. Okay, be careful with the keyword here, major product. Alright, have you finished? Okay, let's have a look at the solution together. Okay. So the first step is to draw the substances first involved in the reaction, right? So you will likely find it helpful to draw the structural formula for the organic reactant. Recall that hydration reaction involves additional water to a unsaturated hydrocarbon. So we have 2-methyl-pent-1-ene plus water here. The second step is to determine where the added entities will attach. During the reaction, the water molecule splits into a hydrogen atom and a hydroxyl group, or /OH. These two entities will be added to the carbon atoms on either side of the double bond in the organic molecule. According to the Markov-Nikov rule, the hydrogen atom will be added to the carbon atom that already has the most hydrogen atoms bound to it. Well, simply the richer get richer. The rich get richer. Therefore, the hydrogen atom will bound to the carbon 1, and the hydroxyl group will bound to carbon number 2. And we can write the whole formula of this reaction, right? The main product will be 2-hydroxy 2-methylpentane. Okay, have a look at the solution here. Let me know if you have any questions, okay? Be careful, when the question asks you to find a major product, you should follow the Markov-Nikov rule. Of course, you will get some other product, but the question asks to predict the major product. Alright, if you don't have any questions, let's have a look at the second part of today's lesson, which is about aromatic hydrocarbons. Michael Faraday was the first person to isolate and identify benzene from a mixture of oils in 1825. Since then, benzene has been used in many commercial products. One of his first uses was an aftershave in 19th and early 20th centuries. In 1903, benzene was used to decaffeinate coffee. It was also used as an anti-knock additive in gasoline to control the ignition of the fuel until the 1950s, when it was replaced by tetraethyl lead. Benzene is also widely used in industry as a solvent in commercial reactions. Testing has identified benzene as a carcinogen and implicated in other health problems. As the hazards of benzene have become known, many of its commercial uses have now been discontinued. So, what is a aromatic hydrocarbon? An aromatic hydrocarbon is an unsaturated hydrocarbon that has a ring structure and a bonding arrangement that causes it to be chemically stable. For example, benzene, or C6H6, is a flat 6-carbon ring with a hydrogen atom bounded to each carbon atom, which is shown here in figure 2. It's the simplest aromatic hydrocarbon. The structural diagram often shows benzene as having 3 double bonds alternating with 3 single bonds. Measurements of the bond lengths between carbon atoms, however, have shown that all 6 bond lengths are equal. If benzene actually had 3 double bonds, then those bonds would be shorter than the other 3. To indicate that all 6 bonds are identical, the structure is shown as alternating between 2 arrangements of double bonds, which is shown here in figure 2b, or simply as a hexagon with a circle inside, which is shown here in figure 2c. The hexagon with the circle indicates that the electrons in the bonds are shared equally between all 6 carbon atoms. Any questions? Alright, next let's have a look at how to name an aromatic compound. There are 2 conventions for naming compounds that include the benzene ring. Which one we use depends on the structure of the other part of the compound. We use the first convention when naming aromatic compounds that have non-carbon substituents or a small alkyl group. In this case, the benzene ring is generally considered to be the parent molecule. The attached functional groups are named as substituents to benzene. If a single group is attached to a benzene ring, we put the name of the group before the root benzene. For example, chlorobenzene, C6H5Cl, has 1 chlorine atom replacing a hydrogen atom on the benzene ring. Compounds made up of a benzene ring with 1 or more halogen atoms attached are called aromatic halides. If 2 or more substituents are bounded to a benzene ring, we number the carbon atoms of the benzene ring starting with the first substituents alphabetically, and continue numbering in the direction of the next closest substituent. Here, figure 3 shows some examples. You can have a look at these examples. And remember, we have a second naming convention, right? In the second naming convention, the benzene ring is considered to be a substituent on a hydrocarbon chain. A benzene ring that has lost 1 hydrogen atom is called phenyl group, PHENYL, phenyl group. Just as a methyl group is like a methane molecule that has lost 1 hydrogen atom. The compound is named using phenyl as a substituent, which is shown here in figure 4. Are you clear now? Okay, so next let's do a tutorial to practice naming and drawing aromatic compounds. Aromatic hydrocarbons with 1 or more simple substituents are named by adding the substituent names to the root benzene. If the substituent is complex, such as a hydrocarbon chain with a multiple bond, consider this the parent group and the benzene ring the substituent. In this tutorial, we will recognize when to use each convention and practice naming and drawing compounds using both conventions. So let's consider the sample problem 1 here. We are given two structural formulas. Name the compounds represented by the following structural formulas. Okay, I'll give you 2 minutes to think about this by yourself, and then we'll have a look at the solution together. Okay? Okay, have you finished? Now let's have a look at the solution to this problem. So for compound A here, the structure has 3 simple substituents, right? So can be named as a substituted benzene. Numbers the carbon items to give the substituents the lowest numbers. Therefore, this compound is called 1-ethyl-2,4-dimethyl benzene. As to the compound illustrated in B, we treat the benzene ring as the substituent. The alkane chain is a hexene, and the benzene ring is bounded to the 3rd carbon item in the chain. Therefore, this compound is called 3-phenyl-hexane. Any questions? Alright, then let's have a look at another sample problem. Draw the structural formula for each of the following compounds. You're given the names of the compounds. A. 1-bromo 2-chloro 4-isobenzene. B. 4,6-diphenyl oct-2-ene. Okay, again, I'll give you some time to have a look at these questions by yourself, and then we'll talk about the solutions together. Alright, let's have a look at the solution together. For question A, first we draw the benzene ring and number the carbon items, right? Next, add the substituents as indicated in the name. A bromine item on carbon 1 and a chlorine item on carbon 2 and a iso group on carbon 4. Then we have the structural formula for this compound, which is shown here on top right. For question B, again, first we draw the parent alkene, which is oct2-ene. Next, add the benzene rings to the 4th and 6th carbon items. Then the structural formula of this compound is shown here on the bottom. Okay, any questions? Alright, make sure you're able to name and draw the aromatic compounds, okay? Alright, next let's discuss the properties of aromatic hydrocarbons. Many aromatic hydrocarbons are liquids at room temperature, while others are crystalline solids. Their symmetrical structure causes them to be nonpolar unless they contain an electronegative substituent, so they are generally insoluble in water. From its discovery and well into the second half of the 20th century, benzene was widely used as a solvent in industrial processes and for dry cleaning cloths. Since the discovery that the benzene is carcinogenic, other chemicals have replaced benzene in the workplace. One replacement compound is methylbenzene, commonly known as toluene, with the chemical formula C6H5CH3, which is shown here in figure 5. Okay, next let's have a look at reactions of aromatic compounds. Its unusual bonding makes the benzene ring behave quite differently from an unsaturated hydrocarbon. Unsaturated hydrocarbons easily undergo addition reactions. However, benzene does not, because its bonds are not really alternating double and single bonds. Each bond in benzene is identical, and they are much more stable than a carbon-carbon double bond. Bond strength is just between that of a single and that of a double bond. In general, therefore, aromatic compounds are much less reactive than alkenes. The hydrogenation of benzene to form cyclohexene requires high temperatures and a catalyst. Benzene does not undergo substitution reactions, in which hydrogen items are replaced by other items, such as halogens. And this concept is illustrated in figure 6. So in figure 6, you can see that the substitution reactions does happen involves benzene. Reaction A is a reaction with chlorine, Cl2. That'll produce chlorobenzene, which is a aromatic halide, and hydrogen chloride. B, reaction with nitric acid, HNO3, which produces nitrobenzene and water. C, reaction with chloromethane CH3Cl produces toluene and hydrogen chloride. Substitution reactions are the characteristic of saturated hydrocarbons, and addition reactions are characteristic of unsaturated ones. Benzene reacts more like a saturated hydrocarbon because of the specialized bonding in the benzene ring. This concept is illustrated in Figure 7. So have a look at all of these reactions, make sure you know the concept here, okay? Alright, so this is the end of today's lesson. Make sure you complete today's homework and submit them before the deadline. Alright, I'll see you next time. Bye.